we can look at something called Vsepr, and that should be changed to VSEPR. I just like saying Vsepr because it's easier than valence shell electron pair repulsion. Well, what this says, it makes perfect sense. Electrons pairs, remember these are negative centers, wish to be as far apart from each other as possible. Okay? It is like charges repel each other. This arrangement of electron pairs around the central atom determines the shape of that molecule. Ah, now electrons in bonds and in non-bonded pairs can be thought of as charge clouds. We call them regions of high electron density. So it is a place around the central atom where we're going to see a lot of electrons. Or, I'm sorry, the presence of electrons. All right? So, to determine the shape, we're going to draw the Lewis structure. Okay, but now we're going to add up the regions of electrons. Now, regions of high electron density can be bonded electron pairs and non-bonded electron pairs around the central atom. And a single bond is the same as a double bond is the same as a triple bond in this case, because all we're looking at is where the electrons are. We don't care about how many, we just want to find the regions. If there are two regions of high electron density, the molecule is going to be linear. Let's look at that carbon dioxide. All right, I have one region of high electron density right here, this whole double bond, and another one over here, the other double bond. Okay? So I have two areas of a high electron density. In order to get these guys as far apart from each other as possible, we want 180 degrees between them. Three regions. This is a flat triangle called a trigonal planar. Let's see. One example is BCl3. What she will do is, let's do one that makes more sense. SO3. Okay? SO3's got two single bonds and one double bond, and it will look like this, like the peace sign, if you will. This is called trigonal planar. He's flat, and these angles are about 120 degrees. So the whole thing adds up to 360. 360 degrees, the whole circle. Okay? Great. And we're not going to go too far with this. We're just going to go to four regions. And we're going to go to four regions because this is so very common. Tetrahedral, tetra means four. And additionally, we have to spend a little time on this. The tetrahedral looks something like somebody sitting on a three-legged stool. We're going to 3 dimensions now. And in this case also, we have to realize that whether we're going to have a region that has all bonded or some non-bonded. When we look at molecular geometries, we only look at the atoms. So if somebody's not bonded, then he's going to affect the shape, but he's not going to be part of the overall geometry for the molecule. How do I say that? I want to say that they will affect how the areas of high electron density are arranged around the central atom, but the actual shape is based upon the bond angles between the different atoms. Let's look at an example. All right. Okay. Actually, we're going to look at these words, trigonal, bipyramidal, bent. Those are the two new ones. All right, so here we are, valence shell electron pair theory. Consider methane. We did methane and we saw that it has single bonds to the hydrogen. Carbon has 8 electrons around it. He's happy. We do the dashes to show single bonds, and these are, we have 1, 2, 3, 4 areas of high electron density. Now it looks like this is 90 degrees, but it's not, you see. 90 degrees would be true if the sky was flat, but he's going into 3 dimensions. So this means into the plane of paper. This one is out of the plane of paper. So we are trying to imitate, using the limitations of a 3-dimensional paper, a 3D structure. 3D structure, and now I can use a lot more space and get them farther apart. I go from not 90, but 109.5. This is called a tetrahedral. And like I say, it's like a little person sitting on a 3-legged stool. I have them wave, but we're afraid that'd be another bond. Okay? Great. Yeah, this is, all right, we've seen this, we've seen this, we've seen this. Now, here is called a ball and stick representation, and the atoms are balls and the bonds are sticks. Great. And then this is called a space filling model for obvious reasons. Okay. All right, and here's a prettier picture. This also shows us our charge density, where the electrons are. This is the solid area, kind of a solid skin we put around the electron clouds. Okay. All right, and it changes color for where the most density is. But still, we have 4 areas of high electron density, in this case single bonds, and they're separated as best they can be in 3-dimensional space. All right, well, here's an example. We can predict the shape of other molecules. So we have CH4, and now we can predict the shape of all of these. They're all going to be tetrahedral. Now, here is the 2 others that start off with 4 areas of high electron density. So we've got 4 electron pairs. But in this case, 3 are bonding, 1 are non-bonding. Nitrogen. If you remember nitrogen, we drew like this when we did the Lewis structure. Again, it looks like it's 90 degrees, but she's not. These again will be close to 109 at 107. And what we call this, we've got a big electron cloud around this pair, which pushes these 3 together a little bit. Okay? And we call this trigonal pyramidal. Pyramids, that gives us an indication of 3D. Triangle is 2D. It's kind of like the difference between a square and a cube. One is 3D, the other is 2D. Anyway, it looks like, I'm not going to even try and draw it. We'll see it in a second. 4 electron pairs again, but this time we've got 2 bonding and 2 non-bonding. Very, very important molecule, water. We can draw water like this. And here's my non-bonded electron pairs. We can even give him little bunny ears if we want to. He's called bent because when you're looking at this with any kind of equipment, you really don't see the electrons. They're too small. What we see is the atoms, and it looks like this. Okay? That's why she's called bent. The presence of the electrons must be there. These non-bonded pairs must be there, or else it would be linear. It is not linear. So somebody is pushing these into a different configuration. Starts off with the tetrahedral with all 4 regions trying to get away from each other. 1, 2, 3, 4. But the actual molecule is called bent. Actually, molecular shape is called bent. Okay. CO2, there she is. Here we go. This is what I did not want to try and draw. So here we have the 1, 2, 3, 4 areas of high electron density. 3 of them are bonded. 1 is non-bonded. We do not show that in this last diagram. We don't show the electrons. We can't see them with any kind of equipment. So, well, you can see atoms, but but you can't see electrons. So the molecular geometry, we differentiate from the electron domain geometry. Electron domain means that they're going to try and get as far apart from each other as possible, and that gives tetrahedral. The molecular says, okay, what is the actual shape of the molecule? And it's based upon bond angles. This guy's called trigonal pyramidal. He is a pyramid, that means a three-dimensional, sitting on a triangular base. And another example. Water. Water's pretty easy. Water is just going to be, we have 1, 2, 3, 4, again, 4 areas, but the actual guy is bent. Okay, so when a molecule absorbs a photon of infrared radiation, it causes the molecule to vibrate, stretch and bend. You can think of these as molecules on weights, or atoms on weights, and the bonds are springs. So when they absorb energy, the spring gets more energetic. And only certain kinds of molecules can absorb infrared radiation. The energy, the molecule then vibrates more strongly, more energetically in response to the absorption of infrared. Remember, infrared is heat energy, heat radiation. And if it can, then it is a potentially greenhouse gas. A greenhouse gas must also have a longish lifespan. If he dies really fast, then he's not doing spam. Good, I'm hungry. Lifespan must be, he must stick around for a while. Okay. And what happens is it gets very energized, and then it releases this heat. As the vibration slows down, it re-releases the radiation. There are many such substances in air besides water and CO2. Methane, N2O, ozone, the CFCs. These are things like freon. They help retain, plus SF6. He's very small. All of these are small compared to our friends CO2 and water in our atmosphere. That's why they get the most press. All right? O2, N2, they do not. Right? Why? Because as they vibrate, there must be a change in charge distribution as they vibrate. As they bend, as they stretch, you've got to see a change in where the electrons are. And for something like O2 and N2, they're perfectly symmetric. So as you can't tell that as one side gets farther, the other side gets farther, and they're perfectly balanced. Right. Okay. What happens now? See how we've got these exactly like springs. There's representative springs. And what different kinds of radiation, this is the electromagnetic spectrum, different kinds of radiation will do different things to molecules. So this is my CO2. Okay? If it gets hit with ultraviolet, energy is higher up here. energy increases this way. Okay. Longer wavelengths means lower energy. Microwaves are very low. They cause molecules to rotate. Infrared causes molecules to vibrate. And again, you see this is supposed to indicate how they are stretching. And they have different modes, different ways they can vibrate. And some are IR absorbent and some are not. But ultraviolet, these are scary because they break bonds. They ionize molecules. That's why you are to avoid ultraviolet radiation, because it can harm your skin. It can cause damage to the cells on your skin. And if you keep doing that, some of these don't just die off, they form precancerous cells. Okay. Not to belabor the point, but here's CO2 again, and these are different kinds of ways it can vibrate. And some of these are infrared, do absorb infrared radiation, and others do not. I don't really need you to know how this which are which, but I do want you to be aware of the fact that what happens is that infrared radiation comes in from the atmosphere during the sun, and then these guys just start vibrating with this guy's in a bend mode. They start vibrating more energetically. Okay? The sun goes down and these start to relax. Okay? All right. And the vibration slows, or the vibration relaxes, and so gives off, or how about re-radiates IR, heat radiation. And this is what the surroundings, this is what heats up our area. So this is giving off then IR. It first absorbs it, and now it's giving it off. And that's what heats up its area.